Okay class, I'm going to discuss with you the tutorial 10, which is related to the force due to magnetic field. So these are the questions. You can get this question from the Google Drive sharing folder under folder tutorial. So for the first questions, so a proton with this one is Q, the charge moving with a speed of 2 × 10⁻⁶ in the y direction through a magnetic field with the magnetic flux density. This one is B, okay, 2.5 unit vector Z Tesla. So you have to calculate the magnetic force Fm for this case. So let's look at what we have. Okay, what are the informations from the questions? First, we know the value of the Q, the speed, and also the magnetic flux. So the illustration will be something like this. You have a charge and it is moving in the y directions, and you have a magnetic field moving is directed in the z directions, and this will be the equation that you have to use to find the force which is experienced by this point charge. And you just fill up the value here, okay, and the speed and also the magnetic flux density. So you multiply all the values together, you will get 150, okay, Newton. And when you cross product the unit vector y and also the unit vector z, you will get positive x. So this one will be the first questions, the answer for the first questions. Let's move on to the second questions. Okay, a proton, so this is the Q value of this proton, is moving with a speed, so this is the speed, through a magnetic field with magnetic flux density of 5. So it experiences a magnetic force of 0.014 newtons. And what is the angle between the magnetic field and the moving directions of proton? Okay, so if you look at this question, they give you the Q, they give you the speed and also the B, but they didn't mention about the direction of this U and also B, but they give you the value of the force. Okay, look at this question. They want you to find the angle between the magnetic field and also the moving direction of the proton. So you need to find the angle. So what you should do? Let's look at the solutions. So these are the information from the questions. Okay, we will still refer to these questions. Okay, but if we want to use this equation, we need to know the direction of the U and also the direction of the B. But if we rewrite this formula, okay, by consider the angle in between the U and B, okay, we can get this equation. Okay, this equation you can get it from your slide as well. And the question give you the force, they give you the Q, they give you the U and B. They want you to find the angle between the B and also the U. Okay, look at the question again. So what is the angle between the magnetic field and the moving direction of the proton? So it's the angle between the B and also the U. Okay, so by simplify this relationship, you can get the angle is equals to 34.06. Okay, let's move on to the third questions. Okay, a charged particle with velocity u is moving in a medium containing uniform electric field and also the magnetic field. So now imagine you have a charged particle, you have a charge. Okay, don't care whether it is a positive charge or magnetic charge, it is moving, okay, with velocity u in a medium that has magnetic field and also the electric field. So the question asks you, what should the velocity of the particle so that this particle experience no net force? Okay, so the total force is 0. So look at this case. So this case you have two fields. One is electric field, the other is magnetic field. So the total force will be the force, okay, from the electric field and also force from the magnetic field, and it should be 0 because no net force. Okay, let's look at the relationship here. So the total force, okay, is the addition or summation of the force due to the electric field and also magnetic field, and it should be 0. So this one is the equation, okay, for the force due to the electric field, okay, and this one is the force due to the magnetic field. Okay, so let's put both of them together by factoring the Q out. Okay, so I try to bring out this Q, and inside the bracket I will left E plus U cross product B. Okay, so we don't know what is the value of the Q. So in order to simplify the solutions, okay, we want to get rid of this Q. So I will divide, okay, the Q at the right hand side. So I cannot only divide it at the right hand side, I have to divide it on the left hand side as well. So because this side is 0, 0 when you divide it with anything, you will still get 0. But here, okay, the formula becomes simplified, no more Q. And this is the relationship between the E and also the UB. So when I move the U cross product B to the left hand side, okay, it will become like this. Okay, and in this question, they didn't give us the value of the B. They give us the value of the H, right? So this one is the H. So let's look at what is the relationship between the B and also the H. Okay, so this is the relationship. So by putting the mu naught H here, okay, and its directions, okay, so this one is the direction of the E. You see, no more arrow above the H because I have specified its direction here, and no more arrow on the E. Okay, so now you have to think the other way around. Okay, normally we'll be given the direction of the U, and then when we cross product with the Y, we will get something, right? But now it's totally different. I don't know what is the direction here, but okay, this direction, when you cross product with the Y direction, I will get the X. So by refer to this cycle, of course this one will be Z, right? Because when the Z, okay, you cross product with the Y, okay, you will get negative X. However, here is positive X. So this one should be negative Z. So you can double check your answer by putting this negative Z here. So when you cross product negative Z with Y, Z with Y, supposedly you will get negative X. And because of this negative here, you will get positive X. So I know the direction of my U should be negative Z. Now let's look at what is the value, okay? We compare the value or magnitude of the U. So now I eliminate this direction. I don't want to look at it. I just want to look at its value and magnitude. So this one will be the relationship. Question asks what is the velocity? So this one will be your velocity. Okay, so by dividing this one, okay, at the right side, I will get this one. So this one I use back the B, okay, I use back the B. So this one will be the value of the velocity. So if you want to specify the U in vector quantity, so this one will be its magnitude and this one will be its directions. Negative, negative, and it will become positive. So this one will be the U, okay. So when the U is in this magnitude and directions, okay, we will get our total force equals to 0. Okay, so this is question 3. Now we refer to question 4. So you have 2 amperes of current elements flows from this point to this point. So you have to draw it out, and it is placed in an environment which contains magnetic field flux density B of this one, and the B is in Y directions. Okay, so you have to predict the direction and magnitude of the force exerted on this current element. Okay, so let's look at the solution. Okay, so this is actually continuing the previous questions. You can double check whether to see the answer is 0 or not. Okay, you can double check it. Okay, but I want to proceed with question 4. Okay, so it is started, okay, at 030 up to 0310. So this one is your current filament, and you have your B in the Y directions. Okay, so for this case, to find the force, okay, exerted on this current element, you need to use this formula. Okay, so you fill up the information that you have. So you have your current, which is 2 ampere, and this is your current element oriented in the Z direction. So its length is dependent on the value along the Z axis. So it will be dz. Current flowing in the positive Z direction. So this one is Z. And the interval will be from 0 to 10 because the length is from 0 to 10. And cross product with the B. Okay, so you just perform the integration as usual and cross product z, okay, with the y, you will get negative x. So this one will be the force experienced by the current filament. Okay, so this is question 4. Okay, let's look at question 5. Okay, so you have two infinite length of wire. So this one is your wires, and they are located as shown in the figure. So determine the force per unit length on both the wires. So you need to find the force, okay, F1 over L, because it is force per unit length, and also F2 over L. So for this case, it is similar as the exercise in when I deliver the lecture that day. Okay, so this one is your current filaments flowing in different directions. Current also different. So I label this one as I1, this one is I2. So first of all, I want to find how much magnetic flux density is produced by current I1. Okay, so this one is your formula, okay, based on the Ampere's law. So for the I1, the current is 15, and I want to know the magnetic field flux density, at position I2. Okay, at this position, what will be is magnetic flux density. So the R will be 3. Okay, will be 3 here, and the DL represent. Okay, this one is a unit vector phi, so it is equivalent to unit vector dl cross product with the unit vector r. So dl depends on the direction of your current. So in I1, so it is in the negative y directions, and your r. Okay, so this one is your source, the source of the magnetic field, and you want to know the magnetic field at all these points here. So your r will be pointing from here to here, okay, from here to here, from here to here. It is in the positive x directions. Okay, so by calculating it, you can get your B1 equals to this one. Next is the B2. Okay, so we have find the magnetic flux density, okay, which is emitted by this I1 at the place I2. Okay, so now we are going to find what is B2. So B2 is the magnetic flux density which is produced by I2. Okay, so you put in the value of I2 inside the formula, and also the distance. So distance is the distance between the I1 and also I2. Okay, so now the magnetic field is produced by this I2, and I want to know the magnetic flux density at the place, at the location of I1. So the distance is still 3. So the difference will be, okay, the R. Okay, so now the source is the I2. Okay, so this one will be the observation point. So your R will be pointing in these directions. Okay, in this direction, in the negative x direction. And for your DL, okay, your DL is pointed in the positive y directions. So you have positive y direction, and this one is negative x. Okay, so you will get 1.33 times 10 power negative 10, and y cross product with negative x, you will get a positive z. Okay, unit vector z. So this one is your B2. Now we have to find the magnetic force experienced by I1. So this one will be our formula. So here we have I1, and here is B2. Okay, B2. So I1 is 15. So look at your I1. So your I1 is oriented in the y direction, and the current is flowing in the negative y directions. And here we define the length of the current filaments. So this is an infinite current filaments. So I simply put a length, okay, for this current filament. I don't know what is the value of the length, and the length might be infinity because it is an infinite line. Okay, so your B2, you get it from the previous calculation here. So you put here. Okay, so when you perform the calculation and also the cross product between the negative y, unit vector y, and unit vector z, you will get this one. Okay, so F1, okay, the force exerted on the I1 per unit length, okay, the length you take it from here, okay, will be this one. Okay, let's look at the force at I2. So this is your I2 here, okay, and now your current is flowing in the positive y directions, and this one is the reading you get it from the previous calculation here. Okay, so you will get this one when you expand the integrations. And since we want to find the force, okay, per unit length, so I will divide length at the left hand side as well as the right hand side, so I get 2 nano. This is the force per length. Okay, now let's look at the last questions. Okay, a square loop of wire in the z equals to 0 plane. So this one is your square loop. Okay, and these are the locations of the end of each of the side of the square. Okay, they are carrying currents 2 milliampere in the field of an infinite filament on the y-axis as shown here. So now I put in this square loop just beside this infinite line, and this infinite line, it has the current 15 ampere. So I have to find the total force on the loop. So in this question, I have to find the force on the side 1. Okay, just assume this is side 1, side 2, side 3, and side 4, and the total force will be the summation from all these sides. Okay, all the force from this side. So let's look at the solutions. So here is the drawing. So I name each of the side 1, 2, 3, 4. Okay, so now we need to find the B1. Okay, the magnetic flux density. Okay, evaluated at side 1. Where is side 1 at this point? Okay, so my I will be I1 and my R will be 1 because there is 1 unit length, okay, distance in between this infinite line and this side 1, so it will be 1. Okay, look at my current of I1 is in the negative y direction, so it is negative y. And what will be my R? Okay, my R is pointing from the source to the observation point, is in the positive s directions, so it will be here. So at side 1, I will experience magnetic flux density of 3 microweber per meters, okay, in the z directions. And let's look at the magnetic flux, okay, at side 3. Why I need to find the magnetic flux at side 3? Because the magnetic flux at this point, side 1 and side 3, they are different because the distance, they are different. Okay, for side 1, the distance R is 1 unit, and for side 3, the distance is 3 unit. So I need to recalculate again the magnetic flux density and for side 3. So same procedure, okay, and this one, it will be 3. Okay, so the magnetic flux density will be 1 microweber per meter square in the z direction as well. Now let's look at how to find the magnetic flux density at side 1. Okay, so here is side 1. So for side 1, okay, this is your side 1, and in the along your side 1 you have current, okay, which is current I2, 2 milliampere. So I will put 2 milliampere here, and the length of your I2 is depend on the value of y, so it should be dy. So now, okay, for the dy, I label it as y directions. Okay, but the length, okay, I can specify it from 2 to 0. Okay, so it will be 2 to 0, or you can put it as negative y and this one to be 0 to 2. Okay, you will get the same answer. And this is the B1, you get it just now by using the magnetic flux density at side 1. Okay, so you will get this reading. Okay, this is for side 1. Okay, next I will move on to the magnetic flux density at side 3. Okay, for side 3, you still have current I2 because the same current is flowing on all the sides. Okay, and this one is the length dy. I still put unit vector y, and this for this interval I need to refer the direction of my current. Okay, look at the side 3. Current is flowing in this positive y direction, and the length is from 0 to 2. Okay, the length of the y from 0 to 2. So it will be from 0 to 2, and you take the value for B1 for side 3. Okay, so you expand it, okay, and solve it, you get the force. Okay, now let's look at the force, okay, due to the side 2 and side 3. So for these four, before we calculate it, we need to know how much flux, okay, the magnetic flux, okay, for the side 1 and also the side 4. Let's look at the location of the side 1 and side 4. Side 2 and side 4. Sorry, it should be 2 and 4. Huh? Okay. So 2 and 4, they are located in these directions, so their magnetic field B will be different at every point. Okay, this point, this point, this point, and this point, all of them, they will have different value of magnetic flux, okay, the B, because they are distant from the source. Okay, from this I1 is different, so they will have different value of B. Okay, so this one, okay, let's go back. This one should be side 2, okay. So I cannot change it. Later I will change this one in your notes. Okay, try to change it. So this one should be 2. Okay, so this one should be 2. Okay, side 2. Okay, fine. So now let's look at how we find the B, okay, for side 2 and side 4. So this is a formula, okay. So this is a DL. Okay, DL, we have to look at the side 2, the length, the DL, okay, is pointed in the positive x directions, and for the the other side 4, it is pointed in the negative x direction. Okay, so we go back here. So this one is the DL. Okay, so DL of sorry, so this one should be the DL for the source I1. Okay, source I1. So let's look at I1. I1 is pointed in the negative y directions, and your R, okay, DL cross with the R, so your R will be from here to here, okay, from here to any point here, and it is pointed in the positive x direction. Okay, so that's why this one is positive x and this one is negative y. So you have to remember, don't confuse. This one DL stands for the direction of the current for I1. Okay, because this magnetic flux is produced by I1. Okay, so when you perform cross product, you get Z. Okay, so now you replace it. Okay, replace this one into this part, okay, to calculate the force. Okay, so for the I2, the current is 2 ampere, okay, flowing in the positive x directions. Okay, so the length of the I2 depends on the value on proxy x, so it will be dx. Now let's simplify, okay, this integration. If you look at this part is r, right? So what is r? R is the distance between the source and also observation point. Okay, so if you want to know the distance, the magnitude, of course you will take the value here minus the value here, right? So here, okay, the magnitude is 1, okay, and here the value is 0. So normally you will take the value here minus here equals to 1. But for every point here, okay, you might represent it with a parameter or variable. Okay, here I put parameter x. So if you want to know the R, will be to taking the value of x minus 0 origin. Okay, so if you simplify these two things and replace this one with the x, okay, it will be like this. Okay, so now the dx is the length of the I2 for side 2. So it will be from 1 to 3. Okay, so you perform these integrations. Okay, so you can press calculator for this one actually. Okay, you don't need to perform this one. So you will get your value equal to this. So let's look at the side 4. So this one will be your side 4. Okay, the side 4 will be negative of side 2. Okay, why? Okay, basically if you look at this one, this part, okay, it will be the same. Okay, same thing. Okay, so the I1 still in negative y direction, and the unit vector R, okay, is still in the positive x direction. No effect, okay, no change on this side. But look at this one. So this one is the L, the length of I2 for side 4. So if you look at side 4, okay, it's this one, right? Now the I is flowing in different direction compared to the side 2. This one is positive x and this one is negative x. So if you put one more negative here, okay, so the overall things will become positive. okay, will become positive. So when we add all the total, when we add all the force from side 1, side 2, side 3 and side 4 eventually, we will only actually consider the force, okay, due to the side 1 and also side 3, okay. So it will be negative 8 newton, okay, should be a Newton here, okay, Newton here. Okay, so this one is the explanation for the tutorial week 10.